NASA's Psyche spacecraft has captured rare observations of the interstellar comet 3I Atlas while traveling toward its main mission target. These new images, taken from tens of millions of miles away, are helping scientists refine the comet's path and study the faint coma surrounding its nucleus. It's a straightforward but important update. A mission built to study a metal-rich asteroid is now contributing valuable data about a visitor from another star system. In this video, we will break down what Psyche saw, why it matters, and what comes next. Let's get started. When astronomers first detected 3I Atlas in July 2025, they quickly confirmed that its hyperbolic trajectory placed it among the rarest objects ever observed, an interstellar comet arriving from outside the solar system. Only 2 confirmed interstellar visitors had been seen previously: Oumuamua in 2017 and Comet 2, I/Borisov in 2019. So the opportunity to study a third object immediately drew significant scientific interest. Unlike the earlier cases, 3I Atlas was bright enough and active enough to allow for sustained monitoring as it moved inward. That monitoring expanded unexpectedly in September 2025, when NASA's Psyche spacecraft, still on its long journey toward the asteroid it was built to explore, found itself positioned to observe the comet. Over an 8-hour period, Psyche's multispectral imager captured 4 images of 3I Atlas from a distance of roughly 33 million miles. At that range, the comet appeared faint, but it was still detectable thanks to the imager's ability to capture subtle variations in reflected sunlight. These images are not meant to be dramatic visuals. Their value lies in precise measurement. Each observation provides a highly accurate data point for determining the comet's location and motion. Interstellar objects move quickly and unpredictably through the solar system, and even small improvements in trajectory modeling help researchers better understand their behavior. With Psyche located millions of miles from Earth, its perspective adds a geometric advantage that ground-based and Earth-orbiting instruments cannot provide on their own. In addition to positional data, Psyche's cameras detected a faint coma surrounding the nucleus. At such a large distance, observing the coma confirms that the comet is actively releasing gas and dust even before reaching its closest approach to the Sun. These details help astronomers compare the object's behavior with both solar system comets and other interstellar visitors. The ability to detect these subtle features highlights how deep space missions, even when not designed for comet studies, can contribute meaningful scientific data through opportunistic observations. Meanwhile, telescopes across the world and in space continue tracking 3I Atlas. Psyche's contribution is just one part of a multi-mission effort that includes infrared spectroscopy, high-resolution imaging, and long-term photometric monitoring. Each instrument captures a different aspect of the comet's evolution, and Psyche's vantage point adds a long baseline component that improves the accuracy of the overall dataset. As for Psyche itself, the spacecraft continues along its planned trajectory. It remains on course for a gravity assist at Mars in 2026, which will redirect and accelerate it toward the metal-rich asteroid Psyche, where it will begin scientific orbiting in 2029. The brief interstellar comet observation did not alter the mission plan. It simply demonstrated the flexibility of current deep space operations and how multiple scientific objectives can be supported simultaneously. Interstellar comets are valuable because they carry physical and chemical signatures of the environments where they formed, environments that may differ significantly from our own solar system. Studying them allows researchers to test theories of planet formation beyond our immediate neighborhood using direct material rather than indirect observation. With 3I Atlas, several early findings stand out. One of the most notable is the composition of the coma. Spectroscopic data show a strong presence of carbon dioxide with CO2 levels higher than those typically observed in most solar system comets. Water vapor, carbon monoxide, and oxygen-bearing molecules are present as well, but the elevated CO2 profile suggests formation in a colder region where CO2 ice could accumulate more efficiently. This makes 3I Atlas chemically distinct from both Borisov and most long-period comets originating within our system. Another important observation concerns the comet's changing brightness and color. As it approached the Sun, 3I Atlas shifted from a redder tone to a more neutral one, likely indicating a transition from older, radiation-processed surface material to fresher dust and ice exposed by solar heating. This color evolution has been documented across multiple observing campaigns and is consistent with a layered structure shaped by millions of years in interstellar space. The comet's activity also appears sustained, with dust and gas production increasing more smoothly than seen in many solar system comets, which often undergo sudden bursts or fragmentation events. These characteristics contribute to a broader effort to understand whether interstellar comets follow predictable patterns or represent a wide variety of formation conditions across the galaxy. With only 3 known examples so far, each provides a test point. Oumuamua behaved unlike any comet. Borisov resembled a familiar water-rich comet, and 3I Atlas appears to fall somewhere in between, while introducing its own chemical signature. Understanding these differences helps astronomers refine models of how icy bodies form, migrate, and are eventually ejected from their home systems. Psyche's observations, though limited to distant imaging, contribute by confirming the extent and persistence of the coma and providing measurements of brightness variations along the comet's trajectory. These data help constrain how much dust and gas the comet is releasing and how that activity evolves. When combined with spectroscopic and photometric observations from other assets, the result is a more complete picture of the comet's physical state. In this context, the interstellar origin is significant not just because it is unusual, but because it allows researchers to examine chemical behavior shaped outside the influence of the Sun. Each detail improves our ability to compare early planetary environments across different systems and evaluate whether our solar system is typical or an outlier. The immediate outcome of Psyche's observations is improved trajectory modeling. When a spacecraft provides data from a position far from Earth, it allows scientists to triangulate the comet's path with greater precision. This is especially important for interstellar objects, whose high velocities and unbound orbits make long-term predictions difficult. Even though 3I Atlas poses no threat to Earth, refining its path provides valuable practice for tracking fast-moving objects with unusual origins. This effort ties into broader planetary defense readiness. While interstellar visitors are rare, they demonstrate the importance of rapid detection and coordinated observation. The infrastructure built for monitoring objects like 3I Atlas, from ground observatories to spacecraft collaboration, strengthens our ability to respond to any future object with a potentially hazardous trajectory. Scientifically, the comet will continue to be observed as it moves away from the Sun. Monitoring how the coma fades and how the spectral features evolve will help determine which characteristics are truly interstellar versus those triggered by solar heating. This late-stage behavior is important because it provides insight into how interstellar comets might appear when far from any star, where most of their history unfolds. Looking ahead, astronomers expect that improved survey telescopes will increase the discovery rate of such objects. When that happens, 3I Atlas will serve as a benchmark, a point of comparison for activity levels, chemical composition, and dust behavior. Its well-documented evolution across a wide range of distances from the Sun will make it a reference for evaluating anything new that enters the solar system from interstellar space. As for NASA's Psyche mission, its brief role in observing 3I Atlas highlights how versatile modern spacecraft have become. Missions designed for entirely different objectives can still contribute meaningfully to planetary science when opportunities arise. Psyche now continues toward its own destination, the asteroid Psyche, where it will study one of the most metal-rich bodies ever explored. The data collected from 3I Atlas will remain a small but valuable addition to its scientific legacy. 3I Atlas gives us a rare glimpse into material shaped beyond our solar system. Psyche's distant observations sharpen our understanding of its path and behavior. As it leaves, the data collected will guide future studies of interstellar comets,